In the beginning, there was darkness. Not the darkness we know on Earth, the fleeting absence of light between dusk and dawn, but a darkness absolute and primordial, stretching across distances so vast that human language strains to contain them. Quigs strains to contain them. Picture yourself suspended in that void, weightless and still, surrounded by nothing but the faintest whispers of light from objects so distant they exist at the very edge of what can be known. This is the frontier James Webb has crossed, mapping regions of space that represent not merely distance, but time itself, folded back toward the moment when everything began. If you're watching this, consider experiencing it in full screen, letting the scale of what we're about to explore fill your vision entirely. And if this journey resonates with you, subscribe to follow more explorations at the boundaries of human knowledge. The James Webb Space Telescope has accomplished something that sits at the intersection of technological achievement and philosophical revelation. It has mapped the deepest region of the universe ever observed by human instruments, peering so far into the cosmic ocean that the light reaching its mirrors left its sources more than 13 billion years ago, when the universe itself was barely 500 million years old. To understand what this means requires us to dismantle our everyday assumptions about sight, about distance, about the very nature of observation itself. When we look at something distant on Earth, we see it as it was moments ago. The delay between light's departure and arrival negligible across terrestrial scales. But in the cosmos, this delay becomes the central fact of observation. This delay. Light travels at a fixed speed, approximately 300,000 kilometers per second. And while this seems instantaneous in our daily experience across cosmic distances, it transforms observation into archaeology. Every photon that reaches us is a messenger from the past. And the farther its journey, the older its message. The James Webb Space Telescope exists specifically to intercept these ancient messengers, and it does so with instruments of staggering sensitivity. Positioned at a gravitationally balanced point called Lagrange 2, approximately 1.5 million kilometers from Earth, Webb orbits not our planet directly, but the Sun, maintaining a constant alignment that keeps Earth, Moon, and Sun always behind its massive sun shield. This configuration is not decorative, but essential. Webb observes in infrared wavelengths, detecting heat rather than visible light, and to perceive the faint infrared glow from the universe's earliest structures, its instruments must be kept colder than the objects it observes. The 5-layered sun shield, each layer thinner than a human hair, but collectively forming a barrier the size of a tennis court, creates a temperature difference of more than 300 degrees Celsius between its hot and cold sides, allowing the telescope's mirror and instruments to cool to approximately minus 230 degrees Celsius, just 40 degrees above absolute zero. At this temperature, the telescope's own heat signature becomes negligible, allowing it to detect infrared radiation so faint that collecting enough photons to form an image requires exposures lasting hours or even days. The primary mirror, composed of 18 hexagonal segments of gold-coated beryllium, spans 6.5 meters in diameter, a collecting surface that gathers infrared light with unprecedented efficiency. Efficiency. Each segment is individually adjustable, controlled by tiny motors that position them with nanometer precision, effectively turning 18 separate mirrors into one perfect optical surface. This precision is necessary because at infrared wavelengths, any imperfection in the mirror's shape would scatter light and degrade the image, blurring the already faint signals from the universe's earliest epochs. When we say James Webb has mapped the deepest region of the universe ever observed, we are speaking of depth in a very specific sense, not depth measured downward, as we might measure the depth of an ocean, but depth measured backward, in time. The universe has no center, no edge in the conventional sense, but it does have a temporal horizon, a limit to how far back in time we can observe, set by the age of the universe itself and the speed of light. The Big Bang occurred approximately 13.8 billion years ago, and in the time since, light from the earliest structures has been traveling toward us. The deepest observations are those that capture light from objects that existed when the universe was youngest, light that has spent most of cosmic history crossing the expanding space between its source and our instruments. But there is a complication that transforms this simple picture into something far more profound. The universe is not static. It is expanding and has been expanding since the moment of the Big Bang. This expansion does not mean galaxies are moving through space away from each other, though that is a common misconception. Rather, space itself is expanding, stretching the fabric of the cosmos and carrying galaxies along with it. For light traveling through this expanding space, the expansion has a measurable effect, stretching the light waves themselves, shifting their wavelengths toward the red end of the spectrum in a phenomenon called cosmological redshift. The farther light travels through expanding space, the more it is redshifted until light that was emitted as ultraviolet or visible radiation arrives at our telescopes as infrared, stretched by the expansion that occurred during its journey. This is why James Webb observes in infrared. The light from the earliest galaxies emitted when the universe was young, and those galaxies were relatively close to the matter that would eventually become the Milky Way, has been stretched by more than a factor of 10 during its journey, shifting from visible wavelengths into the infrared. To see these galaxies at all requires an instrument designed specifically to capture infrared light with extraordinary sensitivity, and this is precisely what Webb was built to do. Its infrared capabilities allow it to detect objects with redshifts exceeding 13, meaning the wavelength of their light has been stretched by a factor of more than 13, corresponding to light emitted when the universe was less than 400 million years old. The mapping that Webb has accomplished represents the culmination of decades of planning, engineering, and careful observation. The telescope has targeted specific regions of the sky, areas chosen for their relative emptiness in visible light, regions where foreground stars and nearby galaxies do not overwhelm the faint signals from the distant universe. One of the primary observing programs involves deep fields, images created by pointing the telescope at a single patch of sky and collecting light for extended periods, allowing the faintest possible objects to accumulate enough photons to be detected. These deep fields build on a tradition established by the Hubble Space Telescope, which created its own deep field images by staring at apparently empty regions of space for days at a time, revealing thousands of previously unknown galaxies in patches of sky no larger than a grain of sand held at arm's length. Webb's deep fields go further, reaching deeper into time and space than Hubble could achieve. Where Hubble detected galaxies from when the universe was several 100 million years old, Webb routinely observes galaxies from when the universe was less than 300 million years old, and in some cases has detected candidate galaxies that may date to even earlier epochs, perhaps as early as 200 million years after the Big Bang. These observations push against the very limits of what we can observe in principle, approaching the era before the first stars ignited, when the universe was truly dark, filled with neutral hydrogen gas that had not yet been ionized by starlight. To understand what it means to map these regions, we must understand the nature of cosmic structure itself. The universe did not emerge from the Big Bang uniform and smooth. Quantum fluctuations, in the first instance of cosmic history, seeded tiny variations in density, regions where matter was slightly more concentrated than average. These density variations, though minuscule at first, were amplified by gravity over hundreds of millions of years. Denser regions attracted more matter, growing denser still, eventually collapsing into the first stars and galaxies. The pattern of these density variations, imprinted in the distribution of matter across the cosmos, reflects the initial conditions of the universe and the physical processes that governed its early evolution. When Webb maps the deepest regions of the universe, it is effectively mapping this large-scale structure as it existed in the universe's infancy. Each galaxy detected in these deep observations represents not merely a single object, but a marker of the underlying distribution of matter. A bright beacon illuminating a node in the cosmic web. By cataloging the positions, brightnesses, colors, and spectra of thousands of these early galaxies, astronomers can reconstruct the statistical properties of the early universe, measuring how clustered galaxies were at different epochs, how rapidly they formed stars, and how their properties evolved over cosmic time. The process of creating these maps begins with raw data, photons striking Webb's detectors after their billion-year journey across space. The detectors themselves are marvels of engineering, arrays of mercury, cadmium, telluride photodiodes that convert incoming infrared photons into electrical signals. Each photon that strikes a detector element knocks loose electrons, creating a tiny current that can be measured and recorded. But the signal from distant galaxies is extraordinarily weak. A single distant galaxy might contribute only a few photons per hour to the detector, barely distinguishable from the background noise created by cosmic rays, stray light, and the detector's own thermal fluctuations. Thermal fluctuations. To extract real signals from this noise, observations are repeated multiple times, and the images are carefully combined, aligning them with sub-pixel precision. And this process, called stacking or co-addition, can transform seemingly empty frames into images rich with faint galaxies, each one a barely perceptible smudge of light against the darkness. But even after stacking, the work of creating a map has only begun. Each detected object must be analyzed to determine whether it is genuinely distant or merely faint and nearby. This distinction requires measurements of the object's color, or, ideally, its spectrum. Color measurements involve observing the same region of sky through multiple filters, each transmitting a different range of infrared wavelengths. A distant galaxy, its light heavily redshifted, will appear much brighter in redder filters than in bluer ones, because its visible light has been stretched into the infrared. By comparing the brightness of an object across multiple filters, astronomers can estimate its redshift and thus its distance and age. But colors alone can be ambiguous. A faint red object might be a very distant young galaxy, or it might be a much closer old galaxy whose stars have aged and reddened, or even a star-forming galaxy whose light is reddened by dust. To break these degeneracies, Webb carries a spectrograph, an instrument that splits light into its component wavelengths, creating a spectrum that reveals the detailed fingerprint of the light's source. Spectra contain absorption and emission lines, features created when light interacts with atoms and molecules in the galaxy's stars and gas. These lines occur at specific wavelengths determined by atomic physics, but in distant galaxies, they are redshifted along with the rest of the light, appearing at longer wavelengths than they would in a laboratory. By measuring the precise wavelengths of these lines and comparing them to their rest frame values, astronomers can determine the redshift with great accuracy, and from the redshift, calculate the galaxy's distance using models of cosmic expansion. The deepest regions Webb has mapped are those where galaxies show redshifts exceeding 10, corresponding to light emitted when the universe was less than 500 million years old. In these regions, the universe was profoundly different from what we see today. Galaxies were smaller, more irregular, less organized into the grand spirals and ellipticals that dominate the present-day cosmos. Star formation rates were higher, with young galaxies converting their gas into stars at prodigious rates, blazing brightly in ultraviolet light that, after redshifting, the intergalactic medium, the space between galaxies, was partially or fully neutral, composed of hydrogen atoms that had not yet been ionized by starlight. This neutral hydrogen is opaque to ultraviolet light, absorbing photons below a specific wavelength and making the universe dark to certain forms of observation. The transition from a neutral to an ionized universe, called the epoch of reionization, is one of the key phases Webb, is designed to study Rovi. Before reionization, the universe was filled with neutral hydrogen left over from the Big Bang. As the first stars and galaxies formed, their ultraviolet radiation began to ionize this hydrogen, creating bubbles of ionized gas that expanded and eventually overlapped, transforming the entire universe from neutral to ionized over several hundred million years. Webb's observations of the deepest regions provide direct evidence of this transition, detecting galaxies that existed during the epoch of reionization and measuring how their light is affected by the neutral hydrogen around them. One signature of this epoch appears in the spectra of distant galaxies. Neutral hydrogen absorbs light at a specific ultraviolet wavelength called Lyman alpha, corresponding to the energy needed to excite a hydrogen atom's electron from its ground state to its first excited state. In a fully ionized universe, there is little neutral hydrogen, and light at the Lyman alpha wavelength passes through space largely unimpeded. But during the epoch of reionization, neutral hydrogen is abundant, and it absorbs Lyman alpha photons effectively, creating a sharp drop in the observed flux blue ward of the Lyman alpha line. This feature, called the Lyman alpha trough or Gunn-Peterson trough, becomes deeper and more prominent as we look further back in time, toward epochs when the universe was more. Webb has detected this feature in the spectra of galaxies with redshifts greater than 7, providing strong evidence that the epoch of reionization was ongoing at those times. By measuring the depth and shape of the Lyman alpha trough across multiple galaxies at different redshifts, astronomers can trace the progress of reionization, determining when it began, how rapidly it progressed, and when it completed. These measurements suggest that reionization was a complex, patchy process, with some regions ionizing earlier than others, creating a cosmic patchwork of ionized and neutral zones that gradually merged over hundreds of millions of years. Someday, trillions of years. The galaxy's web detects in the deepest regions are not merely distant and faint, but also intrinsically small and faint by the standards of present-day galaxies. The first galaxies formed from relatively small concentrations of matter, halos of dark matter, containing perhaps a few billion times the mass of the sun, within which normal matter collected and began forming stars. These early galaxies might contain only millions or tens of millions of stars, compared to the hundreds of billions in the Milky Way, and they occupy regions of space just a few thousand light years across, a fraction of the size of modern large galaxies. Despite their small size, these galaxies are remarkably luminous for their mass, indicating vigorous star formation. The stars forming in these early galaxies are likely very massive and hot, producing copious ultraviolet radiation. Massive stars have short lifetimes, burning through their nuclear fuel in just a few million years before exploding as supernova, enriching the surrounding gas with heavy elements created in their cores. This process of star formation, stellar evolution, and chemical enrichment operates in cycles, with each generation of stars producing elements that are incorporated into the next generation. Over cosmic time, this cycling gradually increases the metallicity of galaxies, transforming their chemical composition from the primordial mixture of hydrogen and helium produced in the Big Bang to the complex blend of elements we find in present-day galaxies like the Milky Way. Webb's observations of the deepest regions allow astronomers to witness the very beginning of this chemical enrichment process. By measuring the spectra of early galaxies, astronomers can determine their modellicities, quantifying the abundance of elements heavier than helium. The earliest galaxies show low metallicities, consistent with having formed only one or two generations of stars. But even at the highest redshifts Webb has probed, there is evidence for at least some heavy elements, indicating that star formation and enrichment began very early, perhaps within the first 1 or 200 million years after the Big Bang. These findings challenge theoretical models of galaxy formation, which must now explain how galaxies could assemble so quickly in the early universe. The standard model of cosmology, called lambda, cold dark matter, describes a universe dominated by dark energy, lambda, and cold dark matter, with normal matter making up only about 5% of the total mass energy content. In this model, structure forms hierarchically, with small objects forming first and gradually merging to form larger structures over billions of years. Early galaxies are expected to be small and faint, consistent with Webb's observations. But the rate at which these galaxies appear to have formed stars is higher than many models predicted. Some of the most distant galaxies detected by Webb are so luminous that they challenge our understanding of early star formation. A few candidate galaxies at redshifts greater than 12, if confirmed, would have luminosities and inferred stellar masses that seem difficult to achieve so early in cosmic history. These objects might represent exceptionally efficient star formation, or they might indicate that our models of galaxy formation need revision, perhaps requiring more efficient cooling of gas, higher star formation efficiencies, or different assumptions about the initial mass function of stars. The distribution of stellar masses that form in each generation. The process of confirming these extreme candidates is painstaking. Initial detections are made using color selection, identifying objects that appear very faint or absent in bluer filters, but bright in redder filters, a pattern consistent with high redshift. But colors alone can be deceiving. Gaminants, such as cool dwarf stars in our own galaxy or dusty galaxies at moderate redshifts, can mimic the colors of high redshift galaxies. Definitive confirmation requires spectroscopy, obtaining a spectrum that shows the characteristic features of a high redshift galaxy, such as the Lyman alpha break or emission lines at redshifted wavelengths. TIG kid wavelengths. Webb spectrograph, called NURSPEC, can observe multiple objects simultaneously using a microshutter array, a grid of tiny shutters that can be individually opened or closed to allow light from selected targets to pass through while blocking light from other sources. This capability allows astronomers to obtain spectra for dozens or even hundreds of galaxies in a single observation, dramatically increasing the efficiency of spectroscopic surveys. Using NIRSpec, astronomers have confirmed many of the high redshift candidates identified through color selection, measuring precise redshifts, and in some cases detecting emission lines from ionized gas within the galaxies. Providing insights into the physical conditions of star-forming regions in the early universe. The emission lines detected in these spectra are particularly informative. Different elements and ionization states produce emission lines at characteristic wavelengths, and the relative strengths of these lines depend on the temperature, density, and ionization state of the gas. For example, oxygen emits strong lines when doubly ionized, producing the so-called emission lines that are among the brightest features in star-forming galaxies. Hydrogen produces the Balmer series of lines, including the prominent H-alpha line. Nitrogen, sulfur, and other elements contribute additional lines, creating a rich spectrum that encodes detailed information about the galaxy's physical state. By analyzing these emission lines, astronomers can estimate properties such as the star formation rate, the metallicity, the ionization parameter, which quantifies the intensity of the ionizing radiation relative to the gas density, and even the presence of active galactic nuclei. Supermassive black holes accreting matter and emitting intense radiation. Some early galaxies show evidence for black holes already present when the universe was less than 1 billion years old, raising questions about how such black holes could grow so massive so quickly. Supermassive black holes containing millions or billions of solar masses are thought to grow primarily through accretion, pulling in gas and dust from their surroundings. But in the early universe, the time available for this growth is limited, and the detection of massive black holes at high redshifts suggests that either accretion was extraordinarily efficient in the early universe, or that black holes formed with larger initial masses than standard models predict. The mapping of the deepest regions thus reveals not only galaxies, but also the seeds of the supermassive black holes that will eventually reside in their centers. These black holes play a crucial role in galaxy evolution, regulating star formation through feedback processes. As a black hole accretes matter, it releases enormous amounts of energy in the form of radiation and powerful outflows, jets of gas and particles that can heat or expel the surrounding gas, suppressing star formation and altering the galaxy's evolution. This feedback process, called feedback, is thought to be responsible for the observed correlation between black hole mass and the properties of the host galaxy, and it may explain why the most massive galaxies in the present-day universe have relatively low star formation rates despite their large reservoirs of gas. Webb's ability to detect and study galaxies and black holes in the deepest regions provides observational constraints on these feedback processes in the early universe. By measuring the prevalence of active galactic nuclei at high redshifts and comparing it to the overall galaxy population, astronomers can determine when, and how black holes began to influence galaxy evolution. Early results suggest that AN are present but relatively rare in the first billion years of cosmic history, implying that feedback may not have been a dominant factor in the earliest galaxies. Instead, star formation appears to have been regulated primarily by other processes, such as supernova feedback, where explosions of massive stars inject energy into the surrounding gas, or by the rate at which gas could cool and collapse to form stars. The deepest regions mapped by Webb also contain information about dark matter, the invisible substance that makes up most of the matter in the universe. Dark matter does not emit, absorb, or scatter light, making it undetectable directly, but its gravitational influence shapes the distribution of visible matter and affects the light traveling through space. One of the key predictions of dark matter models is that it forms a cosmic web, a network of filaments and halos within which galaxies form and evolve. The distribution of galaxies in Webb's deep fields traces this underlying dark matter structure, and by measuring the clustering of galaxies at different redshifts, astronomers can test models of dark matter and constrain its properties. One particularly powerful technique for probing dark matter is gravitational lensing, the bending of light by gravity. According to general relativity, mass warps the fabric of space-time, and light traveling through warped space-time follows curved paths. When light from a distant galaxy passes close to a massive foreground object, such as a galaxy cluster, its path is bent, causing the distant galaxy to appear distorted, magnified, or even multiply-imaged. By studying these lensed images, astronomers can infer the distribution of mass in the foreground object, including the dark matter that dominates its mass. Webb has used gravitational lensing to peer even deeper into the universe than its own sensitivity would normally allow. Galaxy clusters can act as natural telescopes, magnifying the light from galaxies behind them and making faint objects detectable that would otherwise be too dim to observe. This technique, called cluster lensing, has allowed Webb to detect some of the faintest and most distant galaxies known, objects that might be intrinsically less luminous than those detected in blank fields. These lensed galaxies provide a complementary view of the early universe, revealing a population of low-mass, low-luminosity galaxies that might be numerous, but difficult to detect without the aid of lensing. The magnification provided by gravitational lensing is not uniform across the background galaxy. Different parts of the galaxy are magnified by different amounts, and in some cases, the galaxy can be stretched into long arcs or split into multiple images. Arcs or split into multiple images. By modeling the lens and reconstructing the intrinsic shape and brightness distribution of the background galaxy, astronomers can study its internal structure with a level of detail that would be impossible to achieve otherwise. Some of the lensed galaxies detected by Webb show complex morphologies with multiple clumps of star formation or evidence for ongoing mergers, providing insights into the processes driving star formation in the early universe. The deepest regions mapped by Webb also contain a population of objects that may not be galaxies at all, but rather protoclusters, the progenitors of the massive galaxy clusters we see in the present-day universe. Galaxy clusters are the largest gravitationally bound structures in the cosmos, containing hundreds or thousands of galaxies along with vast amounts of hot gas and dark matter. They form at the intersections of filaments in the cosmic web, where the density of matter is highest. In the early universe, these regions appear as overdensities of galaxies, concentrations where the number of galaxies per unit volume is higher than average. Webb has detected several such overdensities at high redshifts, regions where multiple galaxies appear close together in projection and have similar redshifts, suggesting they are physically associated and will eventually merge to form a cluster. Studying these protoclusters provides insights into the formation and early evolution of galaxy clusters, revealing how the most massive structures in the universe assembled over time. The galaxies in protoclusters tend to be more massive and more actively star-forming than field galaxies at the same redshift, suggesting that the dense environment accelerates galaxy growth, at least in the early stages. Over cosmic time, however, the environment of a galaxy cluster becomes hostile to star formation. The hot intracluster gas can strip the cold gas from infalling galaxies, a process called ram pressure stripping, shutting down star formation and transforming star-forming spiral galaxies into quiescent ellipticals. Additionally, galaxies and clusters experience frequent gravitational interactions and mergers, which can trigger starbursts or disrupt the galaxies entirely. The net effect is that by the present day, most cluster galaxies are old, red, and relatively devoid of ongoing star formation, a stark contrast to the vigorous star-forming protocluster galaxies Webb observes in the deepest regions. The mapping of these deepest regions is not merely an exercise in cataloging distant objects, but a form of cosmic archaeology, reconstructing the history of the universe from the fragmentary evidence that reaches us across billions of light years. Each galaxy detected in these deep fields is a piece of that history, a snapshot of a moment frozen in time by the finite speed of light. By assembling thousands of these snapshots, spanning a range of redshifts from the present day back to the first few 100 million years after the Big Bang, astronomers can trace the evolution of galaxies, stars, and large-scale structure across cosmic time, witnessing directly the processes that transformed the simple, smooth universe of the Big Bang into the complex, structured cosmos we inhabit today. The techniques Webb employs to achieve these observations represent the culmination of centuries of advances in optics, detector technology, and data analysis. The telescope's primary mirror, composed of 18 separate segments, is a marvel of precision engineering, each segment ground and polished to within a fraction of a wavelength of light from its ideal shape. Shape, the segments are coated with a thin layer of gold, just 100 nanometers thick, chosen because gold has high reflectivity in the infrared and does not corrode. The coating process itself is a technical achievement, requiring the segments to be cleaned meticulously and then placed in a vacuum chamber where gold atoms are vaporized and deposited onto the mirror surface in an ultra-thin, uniform layer. Surface in an ultra-thin, uniform layer. The telescope's secondary mirror, suspended above the primary on 3 struts, directs the focused light to the science instruments located behind the primary mirror. This folded optical path allows the telescope to achieve a long, effective focal length in a relatively compact structure, crucial for fitting the telescope inside the rocket fairing during launch. The alignment of the primary and secondary mirrors must be maintained with extraordinary precision throughout the telescope's mission, despite the thermal and mechanical stresses of launch and the temperature extremes of space. Webb carries actuators and sensors that continuously monitor and adjust the mirror positions, correcting for any distortions and maintaining optimal focus. The science instruments behind the mirror are themselves technological masterpieces. The near-infrared camera, NIRCam, serves as both the primary imaging instrument and the wavefront sensor used to align the mirror segments. It contains 2 separate channels, one optimized for shorter infrared wavelengths and one for longer wavelengths, allowing it to image a broad range of objects from relatively nearby to extremely distant. The detectors are arrays of mercury-cadmium telluride pixels, each capable of detecting individual photons and measuring their arrival time and energy with high precision. The readout electronics convert the detector signals into digital data, which is then compressed and transmitted to Earth via the Deep Space Network, a system of large radio antennas located around the globe. The near-infrared spectrograph, NIRSpec, provides spectroscopic capabilities, splitting light into its component wavelengths to reveal the detailed properties of distant galaxies. NIRSpec can operate in several modes, including a multi-object mode using the microshutter array, an integral field unit mode that provides spectra for every point in a small field of view, and a long slit mode for high-resolution spectroscopy of individual targets. The microshutter array is a particularly innovative technology consisting of more than 200,000 tiny shutters, each just 100 micrometers on a side, that can be individually commanded open or closed. This allows astronomers to select dozens or even hundreds of targets within a single field of view, obtaining spectra for all of them simultaneously without contamination from nearby sources. The mid-infrared instrument, MIRI, extends Webb's wavelength coverage into the mid-infrared from 5 to 28 micrometers. At these longer wavelengths, the thermal emission from dust becomes prominent, and MIRI can detect the warm dust in star-forming regions and around active galactic nuclei, as well as the light from cool stars and planets. MIRI detectors are arsenic, doped silicon arrays, which must be cooled to even lower temperatures than the other instruments to achieve the required sensitivity. A dedicated cryocooler keeps MIRI detectors at just 7 degrees above absolute zero, allowing it to detect the faint mid-infrared emission from the most distant and dust-obscured objects in the universe. The fourth science instrument, the Fine Guidance Sensor and Near-Infrared Imager and Slitless Spectrograph, FGS NIRIS, serves a dual role. The Fine Guidance Sensor provides the precise pointing information needed to keep the telescope locked onto its target during long exposures, while NIRIS performs specialized observations, including wide-field slitless spectroscopy, which provides low-resolution spectra for all objects in the field of view simultaneously, useful for identifying high redshift galaxies based on the shape of their spectra. NIRIS also includes a mode optimized for studying exoplanet atmospheres, using a technique called transit spectroscopy to measure the absorption of starlight by molecules in the planet's atmosphere. Together, these instruments allow Webb to conduct a diverse range of observations, from imaging deep fields to obtain the faintest possible galaxies, to spectroscopy to measure precise redshifts and physical properties, to time domain observations to study variable sources in transient events. The flexibility of the instrument suite means that a single deep field observation can serve multiple scientific purposes, with imaging used to identify candidates, spectroscopy used to confirm and characterize them, and follow-up observations used to study specific objects in detail. The planning and execution of Webb's observing programs is itself a complex undertaking involving thousands of astronomers worldwide. Observing time on Webb is allocated through a competitive proposal process where scientists submit detailed proposals describing the observations they wish to make and the scientific questions they aim to address. These proposals are reviewed by expert panels, which evaluate them based on scientific merit, feasibility, and the likelihood that the proposed observations will achieve their goals. The highest-ranked proposals are selected for execution, and the observations are scheduled into the telescope's timeline, taking into account constraints such as the target's position in the sky, the availability of guide stars for pointing, and the need to avoid scheduling observations that would point the telescope toward the sun, moon, or Earth, which could damage the sensitive instruments. Each observation is carefully designed to maximize the scientific return within the limited observing time available. Deep field observations, for example, are typically divided into multiple exposures taken at slightly different pointings, a technique called dithering, which helps to fill in gaps between detectors and average out detector artifacts. Detector artifacts. The exposures are also taken with different position angles, rotating the telescope slightly between exposures, which helps to distinguish real sources from instrumental noise and cosmic rays. cosmic rays. The total integration time for a deep field can exceed 100 hours, spread over multiple visits to allow the telescope to observe other targets in between. The data from these observations are transmitted to Earth, where they undergo a series of processing steps to convert the raw detector readouts into calibrated science images and spectra. The first step is to correct for instrumental effects, such as detector bias, dark current, and flat field variations, which are measured using calibration observations taken periodically throughout the mission. The data are then corrected for cosmic ray hits, which appear as bright spots in individual exposures, but are not present in other exposures of the same target. Multiple exposures are combined, aligning them to a common coordinate system and weighting them by their noise properties to maximize the signal-to-noise ratio of the final image. For spectroscopic data, additional processing steps are required to extract one-dimensional spectra from the two-dimensional detector images, a process that involves identifying the location of the spectrum on the detector, tracing its shape, and subtracting the background emission from nearby sources and the sky. The wavelength calibration is established using the positions of known spectral lines or by comparing the observed spectrum to models. The final calibrated spectra are then analyzed to measure redshifts, emission line fluxes, and other properties of interest. The deepest regions Webb has mapped are not static snapshots, but dynamic fields where new discoveries are made with each additional observation. As more data are collected and more sophisticated analysis techniques are applied, the faintest and most distant objects gradually emerge from the noise, pushing the boundaries of what can be observed. Figures of these objects are so faint that they appear in only the longest wavelength images, invisible even to Webb's shorter wavelength cameras, suggesting they are either extremely distant or extremely red, their light dominated by old stars, or absorbed and re-emitted by dust. One of the ongoing challenges in interpreting these observations is distinguishing between different physical scenarios that can produce similar observational signatures. A very distant galaxy, its light highly redshifted, can appear red and faint, but so can a closer galaxy that is intrinsically red because its stars are old, or because dust is absorbing the blue light and re-emitting it in the infrared. Breaking this degeneracy requires careful modeling, comparing the observed colors and spectra to predictions from galaxy formation models and stellar population synthesis codes, which predict the spectrum of a galaxy based on its star formation history, age, metallicity, and dust content. These models are built on our understanding of stellar evolution, the process by which stars form, burn nuclear fuel, and eventually exhaust their fuel and die. Stars form from collapsing clouds of gas, which fragment into dense cores that heat up as they contract. When the core temperature reaches several million degrees, nuclear fusion ignites, converting hydrogen into helium and releasing energy that balances the inward pull of gravity, stabilizing the star. The star then spends most of its life on the main sequence, fusing hydrogen in its core. The duration of this phase depends on the star's mass, with massive stars burning through their fuel in just a few million years, while low-mass stars can burn for tens of billions of years, longer than the current age of the universe. After exhausting the hydrogen in its core, a star evolves off the main sequence, expanding into a red giant as it begins fusing helium and heavier elements in shells around the core. The details of this evolution depend on the star's mass. Low-mass stars eventually shed their outer layers, forming planetary nebulae and leaving behind white dwarf remnants, dense cores supported by electron degeneracy, pressure. Intermediate mass stars may undergo similar evolution, but with more violent mass loss. I-mass stars continue fusing heavier elements until they form an iron core, at which point fusion ceases because fusing iron consumes rather than releases energy. Without the outward pressure from fusion, the core collapses catastrophically, triggering a supernova explosion that blasts the star's outer layers into space and leaves behind a neutron star or black hole. These different evolutionary pathways produce different spectra, and by combining the spectra of stars with different masses and ages, weighted according to the star formation history and initial mass function, astronomers can predict the integrated spectrum of a galaxy. This predicted spectrum can then be compared to observations to infer the galaxy's properties. For the deepest regions Webb has mapped, the galaxies are young with star formation histories spanning just a few 100 million years, and the spectra are dominated by the light from young, massive stars, which are hot and luminous and produce strong ultraviolet emission. But even in these young galaxies, there are signs of complexity. Some show evidence for multiple episodes of star formation, with an older stellar population underlying a younger burst. Others show strong emission lines, indicating the presence of ionized gas heated by ultraviolet radiation from young stars. Still others show broad emission lines, a signature of gas moving at high velocities near a supermassive black hole, indicating the presence of an active galactic nucleus. Each of these features provides a clue to the galaxy's history and the physical processes shaping its evolution. The mapping of the deepest regions also reveals the large-scale structure of the universe at early times. Galaxies are not distributed randomly, but are clustered, concentrated along filaments and sheets that form the cosmic web. This structure arises from the gravitational collapse of the initial density fluctuations imprinted during inflation, the brief period of exponential expansion in the first fraction of a second after the Big Bang. These fluctuations were tiny, with density contrasts of only 1 part in 100,000. But they were amplified by gravity over cosmic time, growing into the galaxies and clusters we observe today. The pattern of these fluctuations is predicted by inflationary models and has been measured with exquisite precision by observations of the cosmic microwave background, the relic radiation from the Big Bang that fills the universe. The CMB shows a nearly uniform glow with a temperature of about 2.7 degrees above absolute zero. but with tiny fluctuations in temperature across the sky, reflecting the density fluctuations in the early universe. In the early universe. The statistical properties of these fluctuations, such as their amplitude and the scales on which they are correlated, provide powerful constraints on cosmological parameters, including the total density of the universe, the density of dark matter and dark energy, and the amplitude and shape of the primordial power spectrum. By measuring the clustering of galaxies at high redshifts, astronomers can compare the observed structure to predictions from cosmological models, testing whether the models that explain the CMB also explain the distribution of galaxies. Any discrepancies could indicate new physics, such as deviations from the standard cosmological model or additional components of the universe that have not yet been accounted for. One of the most intriguing puzzles in cosmology is the nature of dark energy, the mysterious component that makes up about 70% of the universe's mass energy content and drives the accelerated expansion observed at low redshifts. Dark energy was discovered through observations of distant supernovae, which revealed that the expansion of the universe is not slowing down as expected from the gravitational pull of matter, but is instead speeding up. This acceleration implies the existence of a component with negative pressure, which counteracts gravity on cosmological scales. The simplest explanation for dark energy is a cosmological constant, an intrinsic energy density of empty space. But there are alternative models involving dynamical fields or modifications to general relativity. Webb's observations of the deepest regions provide constraints on dark energy by measuring the expansion history of the universe. The redshift of a galaxy tells us how much the universe has expanded since the light was emitted, and by measuring the distances to galaxies at different redshifts, astronomers can reconstruct the expansion history and test models of dark energy. These measurements are challenging because determining distances requires more than just redshifts. It requires standard candles, objects with known intrinsic luminosity, or standard rulers, objects with known intrinsic size. Supernovae serve as standard candles, and the CMB provides a standard ruler, but observations of galaxy, clustering, and gravitational lensing provide additional independent constraints. The deepest regions Webb has mapped are too distant for supernova to be detected reliably, so the primary constraints on dark energy from these observations come from the clustering of galaxies and the effects of gravitational lensing on the CMB, and background galaxies. By measuring how the clustering strength evolves with redshift, astronomers can infer the rate at which structure has grown, which depends on both the matter density and the dark energy density. If dark energy is constant, as in the cosmological constant model, it has negligible effect at high redshifts, and structure growth is determined primarily by matter. But If dark energy evolves over time, as in some alternative models, it could affect structure growth even at high redshifts, and this would be detectable in the clustering measurements. The process of mapping the deepest regions is ongoing, with new observations continually refining and extending our knowledge. Webb's first deep field image, released to the public in the summer of 2022, showed a region of sky known as SMACS 723, a galaxy cluster that acts as a gravitational lens, magnifying background galaxies. The image revealed thousands of galaxies, including some of the most distant ever observed, and it provided a stunning demonstration of Webb's capabilities. Subsequent deep fields have targeted other regions, including fields observed previously by Hubble, allowing direct comparisons between the two telescopes and revealing the new populations of galaxies that Webb can detect thanks to its infrared sensitivity. One of the most ambitious observing programs is the JADE survey, the James Webb Advanced Deep Extragalactic Survey, which combines deep imaging and spectroscopy to study galaxy formation and evolution across cosmic time. JADES targets two fields, the Hubble Ultra Deep Field and a field in the Goods South region, observing them with multiple filters to measure galaxy colors and with near-spec to obtain spectra for hundreds of galaxies. The survey has already detected and confirmed dozens of galaxies at redshifts greater than 8, including several at redshifts greater than 10, and it continues to push toward higher redshifts, searching for the earliest galaxies that formed in the universe. Another major program, called SEERS, the Cosmic Evolution Early Release Science Survey, has targeted the extended Groth Strip, a well-studied region of sky, with extensive multi-wavelength data from other telescopes. Telescopes. SEERS combines imaging and spectroscopy to study galaxies, active galactic nuclei, and the intergalactic medium across a broad range of redshifts, with a focus on the epoch of reionization. The survey has detected numerous high redshift galaxies and has provided insights into the properties of early star-forming systems, including their sizes, luminosities, and star formation rates. The mapping of these deepest regions is not merely an exercise in cataloging distant objects, but a form of cosmic archaeology, reconstructing the history of the universe from the fragmentary evidence that reaches us across billions of light years. Each galaxy detected in these deep fields is a piece of that history, a snapshot of a moment frozen in time by the finite speed of light. By assembling thousands of these snapshots, spanning a range of redshifts from the present day back to the first few 100 million years after the Big Bang, astronomers can trace the evolution of galaxies, stars, and large-scale structure across cosmic time, witnessing directly the processes that transformed the simple, smooth universe of the Big Bang into the complex, structured cosmos we inhabit today. The techniques Webb employs to achieve these observations represent the culmination of centuries of advances in optics, detector technology, and data analysis. The telescope's primary mirror, composed of 18 separate segments, is a marvel of precision engineering, each segment ground and polished to within a fraction of a wavelength of light from its ideal shape. The segments are coated with a thin layer of gold, just 100 nanometers thick, chosen because gold has high reflectivity in the infrared and does not corrode. The coating process itself is a technical achievement, requiring the segments to be cleaned meticulously and then placed in a vacuum chamber where gold atoms are vaporized and deposited onto the mirror surface in an ultra-thin, uniform layer. The telescope's secondary mirror, suspended above the primary on 3 struts, directs the focused light to the science instruments located behind the primary mirror. This folded optical path allows the telescope to achieve a long, effective focal length in a relatively compact structure, crucial for fitting the telescope inside the rocket fairing during launch. The alignment of the primary and secondary mirrors must be maintained with extraordinary precision throughout the telescope's mission, despite the thermal and mechanical stresses of launch and the temperature extremes of space. Webb carries actuators and sensors that continuously monitor and adjust the mirror positions, correcting for any distortions and maintaining optimal focus. The science instruments behind the mirror are themselves technological masterpieces. The near-infrared camera, NIRCam, serves as both the primary imaging instrument and the wavefront sensor used to align the mirror segments. It contains 2 separate channels, one optimized for shorter infrared wavelengths and one for longer wavelengths, allowing it to image a broad range of objects from relatively nearby to extremely distant. The detectors are arrays of mercury-cadmium telluride pixels, each capable of detecting individual photons and measuring their arrival time and energy with high precision. The readout electronics convert the detector signals into digital data, which is then compressed and transmitted to Earth via the Deep Space Network, a system of large radio antennas located around the globe. The near-infrared spectrograph, NIRSpec, provides spectroscopic capabilities, splitting light into its component wavelengths to reveal the detailed properties of distant galaxies. NIRSpec can operate in several modes, including a multi-object mode using the microshutter array, an integral field unit mode that provides spectra for every point in a small field of view, and a long slit mode for high-resolution spectroscopy of individual targets. The microshutter array is a particularly innovative technology consisting of more than 200,000 tiny shutters, each just 100 micrometers on a side, that can be individually commanded open or closed. This allows astronomers to select dozens or even hundreds of targets within a single field of view, obtaining spectra for all of them simultaneously without contamination from nearby sources. The mid-infrared instrument, MIRI, extends Webb's wavelength coverage into the mid-infrared from 5 to 28 micrometers. At these longer wavelengths, the thermal emission from dust becomes prominent and MIRI can detect the warm dust in star-forming regions and around active galactic nuclei, as well as the light from cool stars and planets. MIRI detectors are arsenic-doped silicon arrays, which must be cooled to even lower temperatures than the other instruments to achieve the required sensitivity. A dedicated cryocooler keeps MIRI detectors at just 7 degrees above absolute zero, allowing it to detect the faint mid-infrared emission from the most distant and dust-obscured objects in the universe. The fourth science instrument, the Fine Guidance Sensor and Near-Infrared Imager and Slitless Spectrograph, FGS NIRIS, serves a dual role. The Fine Guidance Sensor provides the precise pointing information needed to keep the telescope locked onto its target during long exposures, while NIRIS performs specialized observations, including wide-field slitless spectroscopy, which provides low-resolution spectra for all objects in the field of view simultaneously, useful for identifying high redshift galaxies based on the shape of their spectra. NIRIS also includes a mode optimized for studying exoplanet atmospheres, using a technique called transit spectroscopy to measure the absorption of starlight by molecules in the planet's atmosphere. Together, these instruments allow Webb to conduct a diverse range of observations, from imaging deep fields to obtain the faintest possible galaxies, to spectroscopy to measure precise redshifts and physical properties, to time domain observations to study variable sources in transient events. The flexibility of the instrument suite means that a single deep field observation can serve multiple scientific purposes, with imaging used to identify candidates, spectroscopy used to confirm and characterize them, and follow-up observations used to study specific objects in detail. The planning and execution of Webb's observing programs is itself a complex undertaking involving thousands of astronomers worldwide. Observing time on Webb is allocated through a competitive proposal process where scientists submit detailed proposals describing the observations they wish to make and the scientific questions they aim to address. These proposals are reviewed by expert panels, which evaluate them based on scientific merit, feasibility, and the likelihood that the proposed observations will achieve their goals. The highest-ranked proposals are selected for execution, and the observations are scheduled into the telescope's timeline, taking into account constraints such as the target's position in the sky, the availability of guide stars for pointing, and the need to avoid scheduling observations that would point the telescope toward the sun, moon, or Earth, which could damage the sensitive instruments. Each observation is carefully designed to maximize the scientific return within the limited observing time available. Deep field observations, for example, are typically divided into multiple exposures taken at slightly different pointings, a technique called dithering, which helps to fill in gaps between detectors and average out detector artifacts. Detector artifacts. The exposures are also taken with different position angles, rotating the telescope slightly between exposures, which helps to distinguish real sources from instrumental noise and cosmic rays. Cosmic rays. The total integration time for a deep field can exceed 100 hours, spread over multiple visits to allow the telescope to observe other targets in between. The data from these observations are transmitted to Earth, where they undergo a series of processing steps to convert the raw detector readouts into calibrated science images and spectra. The first step is to correct for instrumental effects, such as detector bias, dark current, and flat field variations, which are measured using calibration observations taken periodically throughout the mission. The data are then corrected for cosmic ray hits, which appear as bright spots in individual exposures, but are not present in other exposures of the same target. Multiple exposures are combined, aligning them to a common coordinate system and weighting them by their noise properties to maximize the signal-to-noise ratio of the final image. For spectroscopic data, additional processing steps are required to extract one-dimensional spectra from the two-dimensional detector images, a process that involves identifying the location of the spectrum on the detector, tracing its shape, and subtracting the background emission from nearby sources and the sky. The wavelength calibration is established using the positions of known spectral lines or by comparing the observed spectrum to models. The final calibrated spectra are then analyzed to measure redshifts, emission line fluxes, and other properties of interest. The deepest regions Webb has mapped are not static snapshots, but dynamic fields where new discoveries are made with each additional observation. As more data are collected and more sophisticated analysis techniques are applied, the faintest and most distant objects gradually emerge from the noise, pushing the boundaries of what can be observed. Figures of these objects are so faint that they appear in only the longest wavelength images, invisible even to Webb's shorter wavelength cameras, suggesting they are either extremely distant or extremely red, their light dominated by old stars, or absorbed and re-emitted by dust. One of the ongoing challenges in interpreting these observations is distinguishing between different physical scenarios that can produce similar observational signatures. The deepest regions also provide constraints on the escape fraction of ionizing photons, the fraction of ultraviolet photons produced by stars that escape their host galaxies and contribute to ionizing the intergalactic medium. The epoch of reionization requires a sufficient supply of ionizing photons, and the primary source is thought to be young, massive stars in early galaxies. But not all of the ionizing photons produced by stars escape their galaxies. Many are absorbed by neutral hydrogen within the galaxy or in its immediate surroundings. The escape fraction depends on the structure of the galaxy and the distribution of neutral hydrogen. And it is a key uncertainty in models of reionization. Measuring the escape fraction directly is challenging because the ionizing photons are absorbed by neutral hydrogen along the line of sight, making them undetectable. But indirect measurements can be made by studying the properties of high redshift galaxies and modeling the production and escape of ionizing photons based on their observed star formation rates, sizes, and spectra. Webb's observations of the deepest regions provide the data needed for these models, and early results suggest that the escape fraction may be higher in early galaxies than in present-day galaxies. Perhaps because the galaxies are less massive and have more porous structures that allow photons to escape more easily. The mapping of the deepest regions is also revealing the role of environment in galaxy evolution. Galaxies do not form in isolation, but are embedded in the cosmic web, connected to other galaxies by filaments of dark matter and gas. The density of the environment affects the rate at which galaxies can acquire gas, undergo mergers, and interact with their neighbors In dense environments, such as galaxy clusters and protoclusters, galaxies experience frequent interactions and may be stripped of their gas by the hot intracluster medium, while in low-density environments, galaxies evolve more quiescently with fewer disturbances. Webb's observations of the deepest regions have identified several protoclusters, concentrations of galaxies at high redshifts that will eventually evolve into massive clusters. These protoclusters provide laboratories for studying how environment affects galaxy evolution in the early universe. The galaxies in protoclusters tend to be more massive and more actively star-forming than field galaxies, suggesting that the dense environment accelerates their growth. But over time, as the protocluster collapses and virializes, forming a hot intracluster medium, the environment may become hostile to star formation, transforming star-forming galaxies into quiescent ones. The study of protoclusters also provides insights into the formation of the intracluster medium itself, the hot X-ray emitting gas that fills galaxy clusters. This gas is heated to tens of millions of degrees by gravitational energy released as the cluster forms, and it contains as much mass as all the stars in all the cluster galaxies combined. Understanding how and when this gas is heated and enriched with heavy elements is an important question in cluster formation and Webb's observations of protoclusters, combined with X-ray observations from telescopes like Chandra and XMM Newton, are beginning to provide answers. The deepest regions Webb has mapped represent a frontier of observational cosmology, a boundary between the known and the unknown. Beyond the galaxies detected at redshifts of 13 or 14 lies an era that remains largely unexplored, the so-called Dark Ages, when the universe was filled with neutral hydrogen and no stars had yet formed. The Dark Ages lasted for perhaps 100 or 200 million years, from the recombination epoch, when the universe cooled enough for electrons and protons to combine into neutral atoms, to the formation of the first stars. During this time, the universe was truly dark, with no sources of light except the fading glow of the cosmic microwave background. Observing the Dark Ages directly is extraordinarily difficult. because there are no luminous sources to detect. The neutral hydrogen emits radiation at a wavelength of 21 centimeters, corresponding to a hyperfine transition in the hydrogen atom. But this emission is extremely faint and is difficult to detect against the much brighter foreground emission from our own galaxy and from extragalactic sources. Radio telescopes are being developed to attempt this observation, targeting the redshifted 21 centimeter line from the dark ages, but success remains elusive. Webb cannot observe the dark ages directly, but it can detect the first stars and galaxies that emerged from the dark ages, marking the end of this epoch and the beginning of the cosmic dawn. By identifying the earliest galaxies and measuring their properties, Webb provides constraints on when and how the first stars formed, how quickly they enriched their surroundings with heavy elements, and how they began the process of ionizing the intergalactic medium. These observations are pushing toward the very limits of what can be observed with current technology, and they hint at what future telescopes might achieve. Looking ahead, the next generation of telescopes is already being planned, instruments that will build on Webb's achievements and extend observations to even earlier epochs. Epic concepts such as the Habitable Worlds Observatory, a large space telescope optimized for studying exoplanets and their atmospheres, and ground-based extremely large telescopes with mirrors 30 meters or more in diameter will provide complementary capabilities, T's and lithier, probing different wavelengths and different aspects of the cosmos. These future instruments may finally detect population 3 stars, observe the formation of the first, reveal the detailed structure of the intergalactic medium during the epoch of reionization. But even without these future telescopes, Webb's mapping of the deepest regions has already transformed our understanding of the early universe. It has shown that galaxies formed earlier and in greater numbers than many models predicted, that supermassive black holes were already present when the universe was less than 1 billion years old, and that the epoch of reionization was a complex, extended process rather than a sudden transition. It has revealed a universe teeming with activity and structure even at the earliest observable times, a universe that was already well on its way to becoming the complex, diverse cosmos we see today. The deepest regions mapped by Webb are not merely distant in space, but distant in time, windows into a universe that existed more than 13 billion years ago. Light from these regions has traveled across most of cosmic history to reach us. And in doing so, it carries information not just about the galaxies that emitted it, but about the structure of space-time itself, the expansion of the universe, and the fundamental laws of physics that govern cosmic evolution. Every photon detected by Webb's instruments is a messenger from the distant past, a carrier of information that can be decoded and interpreted to reveal the history of the cosmos. This process of decoding is ongoing as astronomers analyze the data, compare it to models, and refine their understanding of the physical processes at work. The mapping of the deepest regions is not a static achievement, but a dynamic, evolving body of knowledge, growing with each new observation and each new insight. As more data accumulate, the picture becomes clearer, the uncertainties shrink, and the questions become sharper, pointing toward new phenomena and new puzzles that demand explanation. And demand explanation. One of the enduring questions in cosmology is the nature of the initial conditions that seeded structure formation, the origin of the density fluctuations that eventually grew into galaxies and clusters. These fluctuations are thought to have been generated during inflation, a brief period of exponential expansion in the first tiny fraction of a second after the Big Bang. Inflation solves several problems in standard Big Bang cosmology, explaining why the universe is so uniform on large scales and yet has the small fluctuations needed to seed structure. The fluctuations are generated by quantum fluctuations in the inflaton field. The field that drives inflation, which are stretched to macroscopic scales by the exponential expansion and become classical density perturbations. The statistical properties of these fluctuations are predicted by inflationary models and have been measured with high precision by observations of the cosmic microwave background. But there are many different inflationary models, each predicting slightly different properties, and distinguishing between them requires ever more precise measurements. Webb's observations of the deepest regions provide an independent test of inflationary predictions by measuring the clustering of galaxies and the distribution of matter at early times. Any deviations from the predictions could point to alternative models of the early universe or to new physics beyond the standard model of cosmology. Another fundamental question is the nature of dark matter and dark energy, the two components that dominate the mass-energy content of the universe, but whose physical nature remains unknown. Dark matter is thought to be composed of weakly interacting massive particles that do not emit or absorb light, but numerous experiments searching for these particles have so far come up empty. Alternative theories propose modifications to gravity rather than new particles, but these theories must explain a wide range of observations from the rotation curves of galaxies to the large-scale structure of the universe to the dynamics of galaxy clusters. Webb's observations of the deepest regions provide tests of dark matter models by measuring the distribution of matter and the growth of structure at early times. Different dark matter models predict different rates of structure, growth, and different clustering properties, and by comparing observations to predictions, astronomers can constrain the properties of dark matter, such as its mass, interaction cross-section, and velocity dispersion. Similarly, observations of the expansion history and the growth of structure provide constraints on dark energy, testing whether it behaves as a cosmological constant or evolves over time. The mapping of the deepest regions also intersects with fundamental physics in other ways. The extreme conditions in the early universe, with temperatures and densities far higher than anything achievable in laboratories, provide a natural testing ground for theories of particle physics and quantum gravity. The formation of the first structures, the synthesis of elements in the first stars, and the generation of gravitational waves from merging black holes all involve physics at the frontiers of our understanding. By observing these processes, astronomers can probe the laws of physics under extreme conditions and test whether our theories hold up in regimes far from everyday experience. One particularly intriguing possibility is that the early universe might contain relics from even earlier epochs, signatures of physics beyond the standard model. For example, some theories predict the existence of cosmic strings, one-dimensional defects in space-time formed during phase transitions in the early universe. These strings would gravitationally lens background light, creating characteristic patterns that might be detectable in deep observations. Other theories predict the existence of primordial black holes formed from density fluctuations in a very early universe rather than from stellar collapse. These black holes could serve as the seeds for the supermassive black holes observed in the centers of galaxies, or they could constitute a component of dark matter. Searching for these exotic phenomena requires careful analysis of large data sets, looking for patterns that deviate from the predictions of standard models. Webb's deep observations provide the data needed for these searches, and as analysis techniques improve and more data are collected, the sensitivity to rare and unusual phenomena increases. Even if no definitive detections are made, the absence of such phenomena provides constraints on theories and helps to rule out or refine models of the early universe. The process of mapping the deepest regions is also a testament to human ingenuity and collaboration. The James Webb Space Telescope is the product of decades of work by thousands of scientists, engineers, and technicians from around the world, representing an investment of billions of dollars and countless hours of effort. The telescope's design, construction, testing, and launch involved overcoming numerous technical challenges, from the deployment of the segmented mirror and sun shield in space to the cooling of the instruments to near absolute zero, to the precise pointing and stability needed for long exposures. The success of the mission is a demonstration of what can be achieved when humanity works together toward a common goal, pooling resources and expertise to tackle problems that no single nation or organization could solve alone. Avalone. The scientific results from Webb are freely available to the global community, with data released publicly after a brief proprietary period, allowing astronomers worldwide to analyze the observations and contribute to our collective understanding of the cosmos. This open approach accelerates discovery and ensures that the benefits of the mission are shared widely. The mapping of the deepest regions is not an end in itself, but a means to understanding the broader story of cosmic evolution, the transformation of the simple, smooth universe of the Big Bang into the complex, structured cosmos we inhabit. This story is written in the light from distant galaxies, encoded in the spectra and morphologies of objects observed across cosmic time. By reading this story, astronomers are reconstructing the history of the universe, tracing the origin and evolution of galaxies, stars, and the elements from which everything we know is made. Yeah. The journey from the Big Bang to the present day spans nearly 14 billion years and encompasses processes on scales from the quantum fluctuations that seeded structure to the vast cosmic web that spans billions of light years and seal years. It involves the formation and evolution of stars, the synthesis of elements from hydrogen and helium into the full periodic table, the assembly of galaxies through mergers and accretion, the growth of supermassive black holes, and their influence on their host galaxy, the ionization of the intergalactic medium by starlight, and the gradual expansion and cooling of the universe driven by dark energy. Each of these processes is interconnected, part of a web of cause and effect that links the largest and smallest scales of the cosmos. The mapping of the deepest regions provides snapshots of this web at different times, allowing astronomers to see how the pieces fit together and how the universe has changed over billions of years. By comparing observations at different redshifts, astronomers can trace the evolution of individual processes and measure how their importance has varied over cosmic time. For example, the star formation rate density rises from the earliest times, peaks at a redshift of around 2 to 3, and then declines to the present day. This evolution reflects the changing availability of gas for star formation, the increasing role of feedback processes that suppress star formation, and the gradual exhaustion of the fuel supply as more and more gas is locked up in stars and remnants. Similarly, the metallicity of galaxies increases over time as successive generations of stars produce heavy elements and enrich the interstellar medium and anja, gradually transforming the chemical composition of the universe from the primordial mixture to the metal-rich gas we observe in present-day galaxies. The mapping of the deepest regions also reveals the diversity of galaxy formation pathways. Not all galaxies form in the same way or at the same time. Some galaxies form early and rapidly, assembling most of their stellar mass within the first billion years of cosmic history. Others form more gradually, accreting gas and merging with smaller systems over billions of years. The environment plays a role, with galaxies in dense regions experiencing more frequent interactions and mergers, while galaxies in voids evolve more yescently. The initial mass of the dark matter halo also matters, with more massive halos forming more massive galaxies, though the relationship is not straightforward due to the complex interplay of baryonic processes. This diversity is a challenge for theoretical models, which must account for the wide range of observed properties and their evolution over cosmic time. Cosmological simulations, which model the formation and evolution of galaxies in large volumes of the universe, are increasingly successful at reproducing the observed properties, but discrepancies remain. and evolution scrimita. Particularly at high redshifts where observations are just beginning to provide robust constraints. Webb's mapping of the deepest regions is helping to close these gaps, providing the data needed to test and refine the models. One of the insights from recent simulations is that the early universe was a violent place, with frequent mergers and interactions driving rapid evolution. Galaxies in the early universe were often irregular and clumpy, lacking the well-defined structures of present-day spirals and ellipticals. Star formation was concentrated in dense clumps within the galaxies, fueled by gas that had not yet been heated or expelled by feedback. These clumps could be gravitationally unstable, fragmenting further or migrating toward the galaxy center, where they might coalesce to form a bulge or feed a central black hole. Over time, as galaxies grew larger and feedback processes became more effective, the rate of mergers and interactions decreased, and galaxies settled into more stable configurations. With spiral galaxies formed as gas cooled and settled into rotating disks, with spiral arms arising from density waves that propagate through the disk. Elliptical galaxies formed through major mergers, violent collisions that disrupted the disks and mixed the stars into a more spheroidal distribution. The morphological diversity we observe in the present-day universe reflects this complex history of assembly and evolution. The mapping of the deepest regions captures galaxies in the midst of this evolutionary process, showing them as they were in their youth before they settled into their final forms. By studying the morphologies, sizes, and kinematics of high redshift galaxies, astronomers can trace the pathways by which different types of galaxies formed and understand the physical processes that shaped their evolution. This is a major goal of extragalactic astronomy, connecting the properties of present-day galaxies to their formation histories, and ultimately to the initial conditions of the universe. Another aspect of the mapping is the identification of rare and unusual objects that do not fit into standard categories. The universe is full of surprises, and deep observations often reveal phenomena that were not predicted by models. Some high redshift galaxies show unusual spectral features that are difficult to interpret, possibly indicating exotic stellar populations or unusual chemical compositions. Others show evidence for powerful outflows, gas moving at thousands of kilometers per second, driven by supernova or active galactic nuclei. Still others appear to be in the process of merging, with multiple components visible in high-resolution images. These unusual objects are valuable for understanding the extremes of galaxy formation and the range of physical processes at work. They often represent brief phases of evolution, transient phenomena that occur on timescales short compared to the age of the universe. First, by identifying and studying these objects, astronomers can learn about processes that are rare or difficult to observe in the present-day universe, but that may have been more common in the past. The mapping of the deepest regions is also revealing the connection between galaxies and their dark matter, halos, the massive, invisible structures within which galaxies form. Dark matter, halos, are predicted to have characteristic density profiles with a cuspy or chord central region and a steeply declining outer regions. The distribution of galaxies within and around these halos provides information about the halo mass and the relationship between halo mass and galaxy properties. A relationship called the stellar mass to halo mass relation. This relation is a key prediction of galaxy formation models and is sensitive to the efficiency of star formation and the effects of feedback. In low-mass halos, supernova feedback can expel gas and suppress star formation, making galaxies less massive than they would be otherwise. But in high-mass halos, feedback from active galactic nuclei can heat the gas and prevent it from cooling and forming stars, again reducing the stellar mass relative to the halo mass. Peak efficiency of star formation occurs at intermediate halo masses, corresponding to galaxies like the Milky Way, where the balance between gas cooling and feedback is optimal for forming stars. Webb's observations of the deepest regions provide measurements of the stellar mass to halo mass relation at high redshifts, testing whether the relation evolves over cosmic time and whether the physical processes regulating star formation have changed. Early results suggest that the relation may be flatter at high redshifts, meaning that low-mass halos form stars more efficiently in the early universe than they do today. Possibly because feedback was less effective or because gas cooling was more efficient in the denser environment of the early universe. The deepest regions also contain information about the reionization process at small scales, revealing the structure of ionized bubbles around individual galaxies and the distribution of neutral hydrogen in the intergalactic medium. The reionization process was not uniform but patchy, with ionized regions expanding around the brightest and most active galaxies and gradually merging to form a fully ionized universe. The size distribution of these ionized bubbles and the topology of the ionized regions provide constraints on the sources of ionizing photons and the clumpiness of the intergalactic medium. Observations of the Lyman alpha line in high redshift galaxies provide one way to probe this structure. Lyman alpha photons are scattered by neutral hydrogen, and the visibility of the Lyman alpha line depends on the amount of neutral hydrogen along the line of sight and in the galaxy's immediate surroundings. Galaxies in large ionized bubbles show strong Lyman alpha emission, while galaxies surrounded by neutral hydrogen show weak or absent Lyman alpha emission. By measuring the fraction of galaxies with detectable Lyman alpha emission as a function of redshift, astronomers can trace the progress of reionization and constrain the sizes of ionized bubbles at different epochs. Webb's spectroscopic observations of high redshift galaxies are providing these measurements, revealing a steep decline in the Lyman alpha fraction at redshifts greater than 7, consistent with the expectation that the universe was more neutral at these times. But there is also evidence for significant scatter, with some galaxies showing strong Lyman alpha emission even at high redshifts, suggesting that they reside in large ionized bubbles, while others show no Lyman alpha, indicating they are surrounded by neutral hydrogen. This scatter reflects the patchiness of reionization and the complex interplay between the sources of ionizing photons and the absorbing neutral hydrogen. The mapping of the deepest regions is an endeavor that combines observation, theory, and simulation, each informing and constraining the other. Observations provide the data, the raw measurements of light from distant galaxies, spectra showing their properties, and images revealing their morphologies. Theory provides the framework for interpreting these observations, connecting them to physical processes and making predictions that can be tested. Simulations bridge the gap between theory and observation, modeling the complex, nonlinear processes that govern galaxy formation and evolution, and producing synthetic observations that can be directly compared to real data. This interplay is essential for progress. Observations alone can catalog objects and measure their properties, but without theory, they lack context and interpretation. Theory alone can make predictions, but without observations, it cannot be tested or refined. Cannot be tested or refined. Simulations provide a way to explore the consequences of theoretical models in realistic scenarios, accounting for the complexity and diversity of the real universe. Together, these three approaches form a coherent framework for understanding the cosmos. Sanding the cosmos. The mapping of the deepest regions represents a major step forward in this endeavor, providing observations of unprecedented depth and quality that challenge and refine our theoretical understanding. The discoveries made possible by Webb are not merely incremental improvements, but transformative insights that reshape our picture of the early universe. The abundance of bright galaxies at high redshifts, the presence of supermassive black holes in young galaxies, the diversity of galaxy morphologies and star formation histories, and the complex structure of the epoch of reionization all challenge simple models and demand more sophisticated explanations. And as the mission continues and more data are collected, the mapping will become more complete, filling in gaps and extending to even earlier times. As the future deep fields will target new regions of sky, providing independent measurements and reducing the effects of cosmic variance, the statistical fluctuations in the number and properties of galaxies due to the limited volume sampled by a single field. Larger samples will enable more detailed statistical studies, measuring the clustering of galaxies, the luminosity function, and the stellar mass function with greater precision. Deeper exposures will push to fainter luminosities, revealing the population of low-mass galaxies that dominate the number counts and may have contributed significantly to the reionization of the universe. The legacy of Webb's mapping of the deepest regions will extend far beyond the mission itself. The data will be archived and made available for future generations of astronomers who will reanalyze it with new techniques and new questions, extracting insights that were not apparent in the initial analyses in the cell. The observations will serve as a benchmark for future telescopes, providing a baseline against which new observations can be compared. And the discoveries will inspire new questions and new missions, driving the continued exploration of the cosmos, San. The cosmos. In the end, the mapping of the deepest regions is about more than just distance or time. It is about understanding our place in the universe, tracing the cosmic history that led from the simplicity of the Big Bang to the complexity of the present day, from the first flickering of starlight in the darkness to the rich tapestry of galaxies, stars, and planets we observe today. It is about pushing the boundaries of what is knowable, reaching toward the very limits of observation and comprehension, and in doing so, revealing the fundamental nature of reality itself. The light that reaches us from the deepest regions has traveled across most of cosmic history, a journey of more than 13 billion years. In that time, the universe has expanded, cooled, and evolved, transforming from a hot, dense, nearly uniform state into a vast, structured cosmos filled with galaxies, stars, and the building blocks of life. The photons that strike Webb's detectors carry the imprint of this history, encoded in their wavelengths, their intensities, and their patterns. By decoding this information, astronomers are reading the story of the universe, a story that is still being written with each new observation. The deepest regions are not static snapshots, but dynamic, evolving systems, and the observations we make today capture them at particular moments in their history. As we observe galaxies at different redshifts, we are effectively watching a movie of cosmic evolution, though the frames are out of order and widely separated in time. By assembling these frames and filling in the gaps through modeling and simulation, we can reconstruct the full narrative, understanding how galaxies formed, how they evolved, and how they came to populate the universe we see today. This narrative is not merely a scientific curiosity, but a profound reflection on the nature of existence. We are made of atoms forged in the cores of stars, stars that formed in galaxies that emerged from the primordial fluctuations imprinted in the Big Bang. Our existence is contingent on a chain of events stretching back to the first moments of cosmic history, a chain that includes the formation of the first stars, the synthesis of heavy elements, the assembly of galaxies, the formation of planetary systems, and the emergence of life. By studying the deepest regions of the universe, we are studying our own origins, tracing the cosmic lineage that connects us to the Big Bang. The mapping of the deepest regions thus serves a dual purpose, advancing scientific knowledge and deepening our philosophical understanding of the cosmos. It reveals the universe as a place of continuous change and transformation, where structures emerge, evolve, and eventually fade, replaced by new structures in an endless cycle. It shows the universe as a place governed by comprehensible laws, where the same physical principles that operate on Earth also operate in the most distant galaxies, where the light we detect follows the same paths predicted by general relativity, and where the atoms we observe are composed of the same particles described by quantum mechanics. And yet, for all that we have learned, the deepest regions remain mysterious. We have mapped them, cataloged their galaxies, measured their properties, but we have not exhausted their secrets. Each answer raises new questions. Each discovery reveals new puzzles. The very existence of bright galaxies at such early times challenges our models. The rapid assembly of supermassive black holes demands explanations we do not yet fully understand. The detailed structure of the epoch of reionization remains to be mapped in full. And beyond the deepest regions we have observed lies an even earlier epoch, the Dark Ages and the first moments of cosmic dawn, which remain largely inaccessible to current technology. The mapping of the deepest regions is thus not an endpoint, but a waypoint in an ongoing journey of exploration. It represents the farthest we have yet reached, the deepest we have yet seen, but it is not the ultimate limit. Future telescopes will go deeper, reaching further back in time, detecting fainter objects, and revealing new aspects of the early universe. The questions we ask will evolve, informed by what we have learned and driven by what remains unknown. And the process will continue, limited only by the fundamental constraints of physics and the ingenuity of those who design and build the instruments to probe the cosmos. The deepest regions mapped by James Webb are a frontier, a boundary between the known and the unknown, the observed and the unobservable. They represent the culmination of human curiosity and technological achievement, a testament to our ability to reach beyond our immediate surroundings and comprehend the universe on the largest scales. They are a reminder of the vastness of the cosmos and the smallness of our place within it. And yet they also affirm the power of the human mind to transcend those limits, to observe and understand phenomena far beyond our direct experience. In the stillness of deep space, where galaxies formed billions of years ago, where light has traveled across the expanding universe to reach us, where the very fabric of space-time carries the imprint of cosmic history, James Webb has mapped the deepest regions ever observed. The data are being analyzed, the discoveries are being made, and the understanding is deepening. The mapping continues, the exploration persists, and the universe reveals itself layer by layer, depth by depth, one photon at a time.